Okay, so let's recall just the setup, right? So we have the free fermion algebra rank 2 is generated, we'll use that notation, it'll be generated by those two fields, phi1 and phi2, subject to these OPE conditions. Phi1 has a first order pole. Phi2 has a first order pole. And then phi2 with phi1, so phi1 with phi2 has a no pole, right? It's trivial, right? No, I didn't. So now let's recall the following that we had before, and that was the automorphism group of Fn is equal to the n-dimensional, well, I guess it's not n-dimensional, it's like the n orthogonal group, right? And this is like pretty easy to see, quote unquote, because let's notice that if G is in the automorphism group of Fn, then G acting on phi of z and G acting on, maybe we use psi of w, should have the same OPE as the original. But we also know that it should have this OPE, the inner product of G phi with G psi over z minus w. That's like the kind of definition of that. But then, like I said, also, since it's an automorphism, this should be the same thing as the original. It should have the same OPE as what you have with just phi and psi, like that. But what that tells us is that this G like fixes the inner product, right? But from linear algebra class, you know that that's equivalent to G being inside of the orthogonal group. That's how you just define an orthogonal linear transformation, is that it fixes like a bilinear form or an inner product, however you want to say that. Okay, so now here's like another kind of fact, and that is the finite subgroups of O2 are either Zn or Dn. So let's say Zn or Dn. So they're either cyclic or dihedral. So cyclic would be generated by this matrix, which is like cos, I'm going to use theta sub n here, and then I'll define that, minus sine theta sub n, and cos theta sub n, where theta sub n equals 2 pi over n. So that's a rotation matrix that just clicks you around 1 over n of the circle, right? That's exactly what that does. And then we know Dn is going to be generated by the Zn thing, so that rotation matrix, so cos theta n minus sine theta n, cos theta n, along with this matrix 1, 0, 0, minus 1. That's a reflection about the x-axis or something, right? So good. And so now you might say, well, I got matrices here, right? But I'm talking about this acting on this like vertex algebra thing. So how do I like kind of put this together? Well, you think about phi1 and phi2 as being kind of the basis vectors here. So that's what we're going to do. So you think that phi1 corresponds to the basis vector 0, 1, and phi2 corresponds to the basis vector 0, 1. I think I said 0, 1 for both, but 1, 0, and 0, 1. So those standard unit basis vectors, right? And now, you know, we might as well like introduce a little bit of notation right here. Let's call this like capital R and just understand that it's like got a subscript of n. And so the fact that it's a n, 1 over n of a rotation matrix, that means that R to the n is the identity, right? It clicks around 1 over n times, right? And so what we want to see is like, how does R act on theta 1 and theta 2, right? But like I said, R looks like a matrix, right? And theta 1 and theta 2 are like generators for the VOA. So what we really want to do is like look at what R does to the vectors. And then after we see what R does to the vectors, we can like translate that back into what R is doing to the things from the VOA. So let's see. R takes this vector 0, 1. Well, let's just do it up. So cos theta n minus sine theta n, sine theta n, cos theta n, hitting the vector 0, 1. So that's going to give us the vector cos theta n here and sine theta n here, right? But then pushed to F2 or whatever, that corresponds to the following kind of action. So that means that R attacking phi1 sends it to this number cos theta n times phi1 plus this number sine theta n times phi2, right? Then, like similarly, R of 0, 1, so that's going to be cos theta n minus sine theta n, sine theta n, cos theta n, 0, 1, that's going to be what? So minus sine theta n, cos theta n, cos theta n. So that corresponds to R attacking phi2 and sending it to this number minus sine theta n times phi1 plus this number cos theta n times phi2. So that in essence is like what's happening before we do any simplification. And it's important to like see what's happening before we do any simplification, because if we like want to do this for a new problem, well, we haven't done the simplification via diagonalization that we have done and like sat on for a couple weeks now. But that's where that came from, is like from this like kind of simplification step, right? Now you could do all of this without some sort of diagonalization. And I think maybe in some cases you kind of have to do that, but for an abelian group, a commutative group, or even this dihedral group, you don't really have to worry about that. You can always diagonalize. There's actually a theorem that says that if you've got an abelian group acting on a vector space, which this is an abelian group acting on a vector space, then if you're in C, that's always, all of the elements of the abelian group are simultaneously diagonalizable. Yeah, it's like from group representation theory or something. And you can see it here with Zn. Well, Zn's cyclic, so it's sort of obvious. You diagonalize the generator and you diagonalize the whole thing. So anyway, like I said, this looks gnarly, right? It would be, I think, kind of hard to write down what things are fixed under the action of Zn if this were the action that we were working with, right? Because we got like cosines and sines in there. Like I said, I think it's possible, but I don't think it's like super worth it. But like we can do that simplification, that diagonalization step. So let's diagonalize our generator R with, let's recall that we're taking Zn to be generated by this matrix R. Could you like kind of keep track of the time? Oh, never mind, there's a clock right there. Okay, so we do that. We first have to find the eigenvectors and eigenvalues. And well, that's all you have to do actually. That gives you the diagonalization, right? But you get the eigenvalues by looking at the characteristic polynomial. And let's recall that for a matrix A, so let's just say A is a matrix, the characteristic polynomial, so maybe we'd call it PAX. So that's going to be the determinant of x times the identity minus A, just like from linear algebra class. And then another thing is if A times x equals lambda times x. So if, in other words, if lambda is an eigenvalue of A with eigenvector, with eigenvector v, we should maybe use that, then we could say that v is in the null space of lambda times I minus A. So that's how you get the eigenvectors, and that's how you get the eigenvalues. The eigenvectors you get from finding the roots of the characteristic polynomial, eigenvalues from finding the roots of the characteristic polynomial, eigenvectors with this null space problem. So let's do that for this, right? So, so if we look at PRX, so that's going to be the determinant of xi minus r. So that's going to be the determinant of, well, we've got a diagonal matrix with x's on the entries. And then we've got this cosine theta n minus sine theta n, sine theta n, cos theta n. But now we can, like, I don't know, subtract those or whatever. Just entry-wise. So we've got x minus cos theta n. We've got sine theta n. The minus signs cancel. We have minus sine theta n, and we have x minus cos theta n. So we're left with something like that, right? But then, I mean, kind of generally, finding the determinant is kind of a bummer. But for a 2x2 matrix, it's not a bummer. Like, it's super simple, right? For a 1x1 matrix, it's even easier. But for a 2x2 matrix, it's not too bad. You just do AD minus BC, colloquially, right? So diagonal multiplied, off diagonal multiplied, and then take the difference. So in this case, notice the diagonal is the same. So we just have x minus cosine theta squared minus sine squared theta. Sorry, that should be plus sine squared theta, right? So then we can multiply that out, and that gives us x squared minus 2 times cosine theta n plus cosine squared theta n plus sine squared theta n. But what's cosine squared theta n plus sine squared theta n? Yeah, it's 1. So we get this thing, x squared minus 2 cos theta n plus 1, right? And so what we want to know where that is 0. That'll give us the eigenvalues. There's actually like kind of a, there's like kind of like this trick to kind of know them already. Like, there's this pattern for when polynomials have complex roots and you factor them into quadratics with only real coefficients, and the form is pretty similar to that. But anyway, so let's find the eigenvalues. So eigenvalues are roots of x squared minus 2 cos theta n plus 1 equals 0, right? Now, I don't know about you, but I can't factor that, right? So I would have to use the quadratic formula to factor that, or maybe complete the square or something. But might as well use the quadratic formula. So that's going to be x equals what? 2 cos theta n plus minus the square root of, that's going to be 4 cosine squared theta n. Wait, no, sorry. Cosine squared theta n minus 4 times a times c. So minus 4. Wait, no, there is a 4 there. Yeah, all over 2, right? Yeah, but check it out. Like, there's a real quick simplification. This 2 is going to annihilate this 2 and those two 4s, right? And then we get cos theta n plus minus the square root of, but that's cosine squared minus 1, but I'm going to factor a minus sign out of it, and we get 1 minus cosine squared theta n, right? If I factor a minus 1 out of that. But what's 1 minus cosine squared? Sine squared. So we get minus sine squared theta n here. But what's the absolute value of negative sine squared? I times sine. So we get cos theta n plus minus I sine theta n. Yeah, and now we can write that using Euler's formula as e to the plus minus I times theta n. So that means we've got two eigenvalues, maybe lambda plus, which is e to the I theta n, and then lambda minus, which is like e to the minus I theta n, right? And now let's find their eigenvectors. All right, so eigenvectors means we have to find the null space of that thing. Well, the null space of that thing is the eigenspace of the corresponding to certain eigenvalue, right, if you remember from linear algebra class. So let's say we are going to do our eigenvector with the lambda plus. So e to the I theta n. Okay. So let's see how that goes. We need to find the null space of what? I said it was e to the I theta n times the identity matrix minus our matrix R, which is cos theta n, minus sine theta n, cos theta n. Something like that, right? And now, in this case, it's probably better to expand the e to the I theta n out again using Euler's formula, because we want it to cancel with some stuff that's already there. You don't have to do that. You could like be kind of extra and write cosine theta in terms of e to the I theta and e to the minus I theta. You could also do that, which maybe I would tend to do because it's like a little bit of a shortcut, but well, let's not do it via the shortcut, I guess. So this is going to be the null space of, so what? This is going to be cos theta n plus I sine theta n, 0. Then we've got this cos theta n plus I sine theta n. And then we have a 0 there, and we're subtracting off this rotation matrix, cos theta n minus sine theta n, cos theta n. So we got something like that, right? So we get like a ton of kind of obvious simplification here. So our cosine terms cancel, and we have I sine theta. And then this is going to give us a sine theta, right? And then this is going to give us a minus sine theta. And this is going to give us an I sine theta. So we have something like that, right? But now, how do you find the null space? Well, let's recall that in linear algebra, you learn that the null space of a matrix doesn't change when you do row reduction, right? So we should probably just row reduce this until it's kind of simple. And then after we row reduce this until it's kind of simple, we can almost just read off the eigenvector by the shape of it, but we'll like do an extra little step in there. So I don't know what kind of row reduction. Well, just remember that to get a row reduction, you want to really put 0 right here, right? That's your first step in a row reduction, is to get a 0 in the bottom right entry, right? Because your goal is to like look for something sort of generally upper triangular, right? Or diagonal or whatever. So let's see, how can we get a 0 in this entry? Well, actually, it's pretty easy. We can do R 2, so that's row 2, minus I times row 1 becomes my new row 2. So I haven't taught linear algebra in a long time, but whenever I teach linear algebra, like I teach this method of like doing row reduction, which is really systematic. So notice my goal is to change row 2, correct? Now for that, I'm going to write my little like kind of equation with row 2 on the left-hand side and on the extreme right-hand side. And then in the middle, I'm going to use, that's the other rows that I can use as a tool. Now in this case, I only have one other row that I can use as a tool because there's only 2 rows. And so sort of the obvious thing is to do that, right? Okay, so let's see, what does that give us? That gives us the null space of, and then now I'm going to look at my row reduction equation and I'm going to say, well, I didn't change row 1, right? Because my key tells me that I haven't changed row 1. So row 1 still looks like I sine theta, and then a sine theta n. And I just realized, you know, I could have just divided the whole matrix by sine, right? But, you know, whatever. We'll do that next. Okay, so now let's see what we get. If we multiply row, oh, and another thing, before I like look at any of the other entries, this is another thing that I like to do. I like to go to the entry that I'm trying to like manipulate and say, well, I already know that's 0. That's why I made this, right? I don't have to think hard about that one. I made this row operation thing so that would be 0. So that means all I have to worry about is the rest of the entries of that row. In that case, it's just one of them, right? So what do I get for this one? Okay, so we got row 2 minus I times row 1. So what do we get if we multiply this by minus I? Yeah, 1 times sine theta, right? What do I get if I add 1 times sine theta to minus sine theta? What do I get if I do 1 times sine theta minus sine theta? 0. So sick, right? Now, this is in almost in, what do they call it in linear algebra class? Like row echelon form or something? Reduced row echelon form. This is almost in reduced row echelon form. The last thing that I have to do is I have to go like up and to the left, and I say, okay, for this to be in reduced row echelon form, what number does this have to be? 1. So now I'll do a row operation to make that occur. So on that row operation will be to divide by I. But, you know, I'm not going to be like, I'm going to multiply by negative I, because dividing by I is the same thing as multiplying by negative I, right? Yeah. Oh, and I'm going to also divide by, and I'm going to also divide by sine, because I keep forgetting to get rid of that thing. Okay, sick. So that's going to give me the null space of, so now I'm going to like do the same kind of thing as I did before. Like, okay, well, I don't have to worry about row 2. Row 2 is not affected by this row operation, right? So I'm just going to go ahead and say, okay, well, row 2 is unaffected. I've got some zeros there. And then also, this entry is automatically 1 because that's why I built my thing, right? And so you look at all of the stuff that's like already taken care of, either by I didn't touch it or by I made this row operation to do this thing in particular. You look at those first, and then you look at what's left over, and you say, okay, well, what like changes from what's left over? So what changes from what's left over? Yeah, negative I. Cool. Now we're ready to like, okay, cool. So the null space of this is equal to the null space of this much simpler matrix, which is in reduced row echelon form. Then furthermore, the null space of this is also equal to the eigenspace with respect to lambda, right? That's how these eigenspaces are defined. They're the null space of this difference thing. Okay. So now if you're probably in linear algebra class at the moment. You can probably just look at that and say what your eigenvector is because you've recently done like a million of these. But since we're not in linear algebra class, let's just see how we would take it home, right? So let's take, I don't know, a vector AB, right, in the null space. Actually, I'm going to like take it way from the beginning. In the eigenspace for eigenvalue lambda, which we just showed was the null space of this simple matrix, right? But what does it mean to be in the null space? Or maybe like this is the same word, but maybe more familiar for kind of more recent classes. It's in the kernel of this matrix. So it's in the kernel of that matrix. So what does it mean to be in the kernel? Yeah, good. You get hit by that matrix and you go to 0. Yeah, it's not exactly going to 0. It's going to the identity element, whatever the identity element here. But here we're talking about like, with respect to like a vector space where addition is the operation, and whenever addition is the operation, the identity element is the 0 vector. So that means that we have 1 minus I 0, 0 times AB is equal to the 0 vector, right? But then by matrix vector multiplication, that gives us this nice equation, A minus I times B, or maybe A minus BI is equal to 0. I mean, generally from a 2 by 2 matrix equation, you would get 2 equations, right? But like we got that row of all zeros, so I mean, I guess we have another equation. 0 times A plus 0 times B equals 0, right? But notice we're going to get a free variable, right? So we have A equals B I, right? And then B is free. Now, again, from linear algebra class, you can look at a matrix in reduced row echelon form, and you can read off what the free variables are in the final thing. The free variables are associated to columns that do not have pivots. So this has a pivot, right? So that means that this is not associated to a free variable. This does not have a pivot, which means it is associated to a free variable. Now I called them A and B instead of x1 and x2, but like the same kind of thing goes here. So that means that B is our chosen free variable. In this case, it doesn't really matter, right? But it's nice to have like a system, right? And that is the system, to be fair, just so that everyone in the class writes down the same answer. So it's easier to grade. But I mean, that's just the situation sometimes, right? Okay, so now since B is free and we're looking for a single eigenvector, right? We only need one. What should we set B equal to? Yeah, but like, what's your favorite number? Yeah, let's set it equal to 1, which means that A is equal to I, which means that I1 is an eigenvector of, actually, I'm going to do something a little wacky. I'm going to set, now we're going to leave it like this. Eigenvector of R, remember R is way up there, with eigenvalue of e to the I theta n. This is I, this is a 1. Okay. And now we could do this whole rigmarole again, but there's actually this like thing that you learn that says that if you have eigenvalue pairs that are complex conjugates, which we do, then the eigenvectors are also complex conjugates. So that means from that fact, we can just read off our entire like eigensystem, if you will, which I don't think they call it like that in class, but like Mathematica calls it this if you like want to find the thing or whatever. So let's say our eigensystem would be something like this. e to the I theta n corresponds to, what did we say, I1, and e to the minus I theta n corresponds to minus I1. And now, next up, now this is not super necessary or whatever, but to make everything kind of work out nice, the OPEs, it's useful to like turn these into unit vectors. So that means that we have to divide them by their length, right? So let's do that. So let's find the modulus of I1. So a modulus of a vector with complex entries, it's not just the square root of the dot product. It's the square root of the dot product of the original vector and the complex conjugate of the original vector. So we have, that's the square root of I1 dotted with minus I1. So what's that dot product give you? What's I times minus I? Yeah, you want to, yes. So it's 2, yeah. Right? Because you just multiply across and then add, right? Okay, so now what we'll do is let's like switch these things out for their associated like unit vectors. So 1 over root 2 minus I1. So something like that, right? Now we can push this back to our VOA setting, right? So let's see, in the VOA setting, we have 1 over root 2 and then minus I1 corresponds to what element of F2? So it's going to be 1 over root 2 and then what? Yeah, so remember what was our translation between like column type vectors to fields? I don't know, maybe it'd be useful. What? I mean, that's part of it. Here, I'm going to change this to plus. So this is I times 1, 0 plus 0, 1, right? But what did 1, 0 correspond to? Phi 1, yeah. And 0, 1 corresponded to phi 2, right? So this corresponds to 1 over root 2 and then I phi 1 plus phi 2, right? And then the other one, so 1 over root 2 minus I1 corresponds to 1 over root 2 minus I phi 1 plus phi 2, right? So that's just like turning those back into our original thing, right? But now, I don't know, I'm like kind of anal and I don't really like, I want the coefficient of the first one to be 1. I just do. I don't know. I just do. So I'm gonna do that by scaling one more time. So I can do it by scaling this first one by just multiplying by minus I, right? So that's going to give me 1 over root 2, and then we have phi 1 minus I phi 2, right? And then this one is going to give me 1 over root 2 phi 1 plus I phi 2. Again, this by scaling by something else, right? And now that motivates us to define the following. So let's define these diagonalized generators, psi 1 to be equal to 1 over root 2 phi 1 minus I phi 2, and psi 2 to be 1 over root 2 phi 1 plus I phi 2. And then let's also define We need like a letter for the e to the I theta sub n. Maybe eta? I don't know. Eta? So no, because omega is like the conformal vector. So that tells us that eta to the nth power is 1, right? So that's kind of the whole point, right? Yeah. Yeah, well, could have done xc. Okay, and now we're like in business, right? So now we can almost forget about everything we've done so far and just say, okay, well, cool. Now we've got F2 is equal to generated by psi1 and psi2 with psi1 of z, psi1 of w is 0. It has no pole. And you can check that like just by doing the same thing. Yeah, exactly. Yeah. I knew you were ahead. And you can check that just by doing this, right? So if you mash this with itself, you'll get 1 minus 1, right? It's kind of, yeah. I mean, essentially you just look at the 0th product, right? And then similarly, psi2 with itself is also 0, but then psi1 with psi2 is 1 over z minus w. So that's how we get there. And depending on what group you're working on, this might be slightly different. You always have to recheck your OPEs after you do this kind of malarkey. It might be kind of way different. And then also we know the following. We know that if R hits psi1, we get eta times psi1, right? That was the whole point here, right? That's what the eigenvector-eigenvalue relationship means, right? Recall that down here, the eigenvector-eigenvalue relationship means that R, our like rotation matrix, if R hits I1, it's the same thing as just simply multiplying by the eigenvalue, right? That's the whole point, right? Okay, and then similarly, R hitting psi2 gives us eta inverse of psi2. And that's like pretty clear, because if eta is this, e to the I theta n, then eta inverse is e to the minus I theta n, which is the other one, right? Okay, so we have that. Then that leads us immediately, and you know, we did this kind of thing before. So the basic, what we'll call the basic invariants of F2Zn are going to be of the following form. So we've got this thing which we called omega AB, which is the normally ordered product of the 8th derivative of psi1 and the bth derivative of psi2, right? We had that thing, right? And then we also had this thing called C1. We had C1 comma n from last time because we did some work with it, but we'll just call it C1 here. And now I'm also going to like and this is something that you see after like working through details, you see that, oh, maybe I should have like named this thing like slightly differently. I'm going to name these indices like in decreasing order, mn, mn minus 1, all the way down m2, m1. Yeah. I think it just like, for kind of where we're going, this actually kind of works a little nicer. Then recall that this is going to be the normally ordered product of the mnth derivative of psi1 all the way down the m first derivative of psi1. And then we had a C2, mn down to m1 as well, which is, I don't know, it's the same thing. Psi2, all the way down m first derivative of psi 2. And how do we know those are invariant? Well, check it out. If r hits this, right, we pick up a eta from the psi 1 term, and we pick up an eta inverse from the psi 2 term. But what's eta times eta inverse? 1, yeah. And then if we have r hit this, we pick up an eta from all of the terms. We pick up n total etas, but that's eta to the n, which is 1, right? And then similarly down here, if we hit this with r, we pick up an eta inverse for all of them, but that's going to give us eta to the minus n, which is 1 over 1, aka 1, right? Yeah. And so these are our basic invariants, right? And so now our goal is to like find a minimal generating set, right? That's like sort of the big thing that we're trying to do, is to minimize this generating set. Right. And I mean, if you recall, how we got that generating set was like look at some things that are happening on polynomials, and then from that I think the technical word is you look at the polarizations of those polynomials, and that gives you this thing. There's like this theorem that says that if you know the generators of a polynomial fixed point algebra, then the polarizations generate the vertex algebra. So just like as a quick thing of that, if r dot x is equal to eta x and r dot y is equal to eta inverse y, then xy is fixed, right? That sort of quadratic. So, but then when we look at all types of quadratics in the vertex algebra, we don't just look at the like generator, we have to look at the derivatives of the generators, right? Because we've got this extra structure. So this is giving rise to this thing right here, like that. And then the same thing here, like this would be like an x to the nth power being fixed, and the polarization of that would, like, you take each of those x's and you put a possibly different derivative on all of them. So that's how you get that. Okay. And then we have some like nice formulas, right? So like, for example, you know, like pretty straightforward calculation that we did shows us that if you take the rth product of the bth derivative of psi 1 with the eighth derivative of, the eighth derivative of psi 1 and the bth derivative of psi 2, you get like what? It was a minus 1 to the a, and then a plus b factorial, and then delta a plus b r. I mean, we've written that down like 1,000 times, right? We have it all committed to memory, I'm sure, right? And then we had like something similar for if you hit like psi 1 into a bigger thing as well, right? Well, actually, let's kind of write all of these down. And then dA psi I, rth derivative, dB psi I is always going to be 0. So we know that's always 0, right? And then from that, you can gain like a lot of other formulas. I don't know, maybe you guys can like help me sort of remember some of these other formulas. Like, I'm sure they're somewhere in the depths. What do we have for like dA psi 1? the rth product hitting like omega m comma n. N is not a good choice. C comma D. I think we have like a formula for that as well. We can just use this thing over here. It's actually like pretty quick. So this is going to be the 8th derivative of psi 1 sub r hitting this cth derivative of psi 1 and this dth derivative of psi 2. Right? But now looking over there, it acts kind of like a derivation, if you will. So that's going to give us what? That's going to give us the 8th derivative of psi 1 sub r hitting the cth derivative of psi 1 and then times the dth derivative of psi 2. So that's like this first bit right here. And you might say, well, where's the normally ordered product? Well, this right here is just a number, so we don't actually need that anymore, right? And then we have minus, because it's plus minus 1 to the parity thing, and that's 1, so we get a minus 1 there because they're both odd. And then here we're going to have psi 1 r hitting the dth derivative of psi 2, and then the cth derivative of psi 1. So that's, anyway, that's just this thing over here, right? So,
you always like say it's just a number. Like, how do you know when it's a normal order versus when it's just
so we know that this is just a number right here because of this formula. Like that's just a number. Yeah. Okay, sick. But now we can like write this down pretty handily. We know that this is 0, right? By formula number 2, and then this is going to be minus 1 to the a plus 1. We get that minus 1 and then that minus 1 too, right? And then a plus d factorial, and then delta a plus d comma r, and then the cth derivative of psi 1. So we get something like that, right? And then furthermore, we can have a similar formula for the bth derivative of psi 2, the r product with omega cd. I think we can just eyeball this. So in this case, this one is going to be the non-zero one, right? And that one is going to be the 0 one. So we're going to pick up a minus 1 to the a, and now it's going to be minus 1 to the b, and then a b plus 1 factorial, and then a b plus c factorial, right? I'm like all discombobulated now. And then a delta b plus c comma r, and then a dth derivative psi 2. We've got something like that, right? Does that seem right? There should be one. Yeah, but one of them gets canceled because we've got different particle types. Are you looking at just like the original with psi 1, or with psi? Because like, look, here we distribute this product to each one, right? But this one's 0. Okay, so this leads to the following. So we have omega 0, 0, and omega, maybe we'll just call it A0, right? We can simplify that, right, using what we've just done, right? So do you have the formula for that? I think yeah. Make sure it's kind of the most recent-ish one. Okay, so let's just do it out. So we've got that, right? So we're going to break the associativity, right? But breaking the associativity, we automatically get 0 for the good term because there's a repeated psi 2. And then after that, we'll have the sum as m is bigger than or equal to 0 of 1 over m plus 1 factorial, right? And then, well, let's just compare it with the, so this is playing the role of A, this is playing the role of B, and this is playing the role of capital C in that formula on the other board. So now inside of here, we're going to have the m plus first derivative of psi 1. And then that's going to be hitting the mth product of psi 2 with, you know, I might as well not even write that down. That's just omega a 0 because we had like a formula for that already. And then this is going to be minus, again, because of the parity thing. And then the m plus first derivative of psi 2. And then we have the mth product of psi 1 with omega a 0. Right? So that's using this. But let's see, we've got like formulas for these now, right? So what's this? So let's see. So what's the mth derivative of psi 2 with omega a 0? So minus 1 to the,
But b is 0, so it's just
yeah, so a factorial delta a comma m, right? And then
with psi 2.
and then dm plus 1 psi 1 with psi 2.
Yeah.
So that's that, right? And then this is going to be minus, so what does that give us? We got a minus here, and then we have a minus built in from that. All right, so what's this?
So negative.
Yeah, negative a plus 1, right? And then a factorial again, right?
No.
Yeah.
Because a in this case is 0, and d in this case is 0.
Oh, yeah, so 0 factorial. 0 factorial. And then,
0m.
and then delta 0m. Delta 0m.
And then psi 1.
And then,
Psi a 1. Delta a. Partial a psi 1. Because c in this case is a.
yeah, the 8th derivative of psi 1. So we've got something like that, but I left off this term right here. Oh, jeez. This is annoying. So minus 1 of the a plus 1, and then the m plus first, and then let's put all our numbers first. And then 0 factorial, which like you said is just 1, and then d delta what? 0m. And then the normally ordered product of the m plus first.
A plus a. Put the a in there. Because remember we get.
Oh, m plus a plus 1?
Yeah.
M plus a
Plus 1.
plus 1.
And then psi 2 psi 1.
Psi 2, and then psi 1. Okay, good. Now we're cooking. But now this simplifies really quickly because notice that this picks out the m equals a term, and this picks out the m equals 0 term, right? So let's see. For the m equals a term, we'll have a factorial over a plus 1 factorial, right? And then for the, and then we'll have what? That's going to be omega a plus 1 comma 0, right? Yeah. And then here for the n equals 0 term, that's going to be minus, sorry, maybe plus minus 1 to the a, just bring that in there. Then for the n equals 0 term, we're going to have 1 over 1 factorial, so that's going to be another 1 factorial, right? And then we're going to have the a plus first derivative of psi 2 with psi 1, right? Now that's not an omega yet. We have to switch it to put the psi 1 first to make it be an omega. So once we switch it, we're going to pick up another minus sign, and that'll be omega 0 a plus 1. So we have that. Okay. So in the end, we have this. Omega 0, 0 on omega a 0 was equal to 1 over a plus 1, omega a plus 1, 0, and then minus 1 to the a, omega 0 a plus 1. Yeah, so something like that. I mean, we're doing it faster and looser this time, right? But like, it's like kind of close enough, right? You can check all these in Mathematica, like if you're actually doing it and we're not just like trying to put everything together in one spot. Okay, so we've got something like that, right? Also, let's recall we had this lemma that said the following. It said that omega a comma b could be written as minus 1 to the b, omega a plus b comma 0, right? Plus the derivative of, I'll just put here, lower weight terms. Right? Remember that? Yeah. We proved that by induction or something, right? It was not that bad. But that means of the omega a, what? 1130. Of the omega a b generators, we only need omega a 0, right? With a bigger than or equal to 1. No, sorry, bigger than or equal to 0. We're allowed to have it be equal to 0 here because they're different shades of particle. Okay, now we use this formula to like finish it all off, right? So now we can maybe do induction by weight, or we could do like some proof by contradiction. We could say, let's suppose we've got the lowest weight element that can't be written in terms of just omega 0, 0 or something like that. Maybe since we haven't done it that way, let's do it that way this time. So let's claim that we only need omega 0, 0. And so what I really mean by that is that the algebra generated by the omega AB, where a and b are bigger than 0, is equal to the algebra generated by omega 0, 0, right? And then, I don't know, like I said, let's do this slightly differently because we haven't done it this way before. But let's, by way of contradiction, suppose this is not true, and pick the omega a 0, maybe like a plus 1, 0, that isn't in this thing generated by just omega 0, 0 with a as small as possible, a minimum. Right? With a as a minimum. But now by star, we have omega a plus 1 comma 0 is equal to, actually, we can do one more thing here, right? We can write this thing over here as 1 over a plus 1, omega a plus 1 comma 0, and then we can use this formula right here, right? So that's going to give us another minus 1 to the a plus 1. But that's going to change this to a plus, I believe. So plus omega a plus 1, 0 plus derivative of lower, right? And so that's just, I know like it's further down in the timeline, but I'm like just fitting it in right there. That's just applying that formula like immediately, right? And it's pretty cool that like all those minuses cancel. Or like we made a typo and they shouldn't have canceled. But it's like, again, it's like the idea is right. But now let's see what we can do. We have, oh no, but I remember this equation exactly. So we have 1 over a plus 1 plus 1 times of omega a plus 1 comma 0 equals the normally ordered product of omega 0, 0 and omega a 0 plus the derivative of lower things, right? But then by our assumption right here, the minimality of a, these things are smaller than a, include things that are smaller than a, right? So since these are smaller than a, they're in this generating set, right? So this is inside of the thing generated by omega 0, 0, but that's a contradiction, right? Contradicting the fact that we have something outside of it. But then that means that we only need the omega 0, 0, right? So now let's see where we are. Is that correct, that clock? Yeah. Okay.
Well, it's 17. Yeah. Yeah.
Okay, cool. Okay, so let's see. So far, I almost wrote so raf. So far, we need omega 0, 0 and C1. Maybe let's just put Ci, Mn down to M1 with I in 1, 2. And we might as well say Mn is bigger than Mn minus 1, M1, which is bigger than 0, right? We might as well put them in that order, right? And now we could do like kind of a similar lemma to show this. We actually only need C, I'll just use 1 here in place of I, M1 all the way down to Mn minus 1 and a 0 there, right? And again, we could like prove this again by way of contradiction. We could like really overuse that proof technique today. So by way of contradiction, suppose not, and A is the smallest, so that C1, M1 down to Mn minus 1 comma a plus 1 can't be written with terms, maybe, I don't know, ending in 0. That's not a perfect way of writing it, but that's just like something ending with a 0 right there, right? Let's say it's this. A is chosen so that that thing right there is the smallest rightmost thing that can't be written ending in a 0. But immediately that blows up in our face. I mean, we're proving by contradiction, so we want it to blow up in our face. Just by taking a derivative, let's take a derivative of c1 m1 down to mn minus 1 a, right? And that's going to give us, let's see, c1 m1 plus 1 dot 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 down to mn minus 1 with a plus c1 m1 m2 plus 1 all the way down mn minus 1 comma a dot 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 down to c1 m1 down to mn minus 1 comma a plus 1, just by the product rule, right? But look, we can solve for c1 m1 mn minus 1 comma, I just reversed our naming convention again, but I don't know, when we need it we'll go back to the other one, I promise. We can write this with an a plus 1 in terms of things that are, and I'm just going to put OK here, but by OK I mean they can be written in terms of the other thing, right? Because the a plus 1 was the smallest one that couldn't, right? Yeah. But look, it's written in terms of things that are got smaller things right there. That means they all could, right? But this is written in terms of things that all can be written with a 0 at the end, right? But that means that it can also be written as a thing with a 0 in the end, and that's a contradiction, right? Yeah, so meaning that yes, we can really just put a 0 there, right? We're being real math today and doing non-constructive proofs, right? Which is pretty dope sometimes, right? I mean, there's always a nasty calculation in the back of the non-constructive proof, but still okay, and then, well, we're gonna stop for my meeting and maybe we'll look at the rest of it. Okay, so now let's recall that we got down to there, and then we also had this formula that we developed yesterday. So I won't go through the details of this one like I did for the other one, because it's kind of newer, and I'm gonna write it like this. No, let's put a 0 here, right? We can always put a 0 there, right? So now, someone want to remind me what this is? It was some j, sum as j goes from 1 to n. And then a 1 over mj plus 1, right? And then c1 mn mj plus 1 m2 0, right? Is that correct? Does that seem right? Yeah. Okay. Cool. Now let's observe. No, because we did some commuting, yeah, to get rid of it. I thought that was kind of a nice way to do that. Now let's note this. at omega 0, 0 with C1. Now let's go mn down to mk plus 1, and then k minus 1, 2, 1, 0. Let's say we're doing that. Now, this seems like sort of a kind of gnarly. So let's like look at maybe one kind of example of it with like n equals 5 or something. So this would be like m5, m4, and then 3, 2, 1. That would be an example with like n equals 5, k equals 3. Wait, sorry. All right, sorry, this should be sorry, this should be k plus 2. So this would be so this would be 2. It is recorded. Yeah. So 2, 1, 0. There we go. Like that, right? So the important thing is we have n total things in the index here, right? It's a little awkward because it's starting at 0, though. Okay. So now let's observe that something kind of interesting happens if we do this. Let's observe that we have the following. So omega 0, 0, and then C1 of mn down to mk plus 2, and then k minus 1 down to 1, comma 0. Okay. So that's going to be equal to the sum as j goes from 1 to k plus 1. Actually, let's split it up into a couple of pieces. So I'm going to split it up into the sum as j goes from 1 to k. So, and then let's color code this. So the sum j goes from 1 to k is acting on these, right? And then plus just the k plus 1 term. Okay? And then plus, and then I'm just going to put a box here, and we'll write it all up there, plus the sum as j goes from k plus 2 up to n. So let's see. I've got this yellow box, so I'll just use the yellow box is what's acting on this one, right? And then this blue thing is acting on all of these, right? Okay. So that's how we want to like think about splitting it up. So I'm just going to bring this back up here. C1, M1 down to MK plus 2, K down to 1, 0. It's kind of a pain, but I think like it's useful to write it all out at least once. Now, tell me about this purple sum. It goes to 0, yeah, because the purple sum is raising each of these indices one at a time. But anytime you raise one of these indices, it's going to coincide with another one, right? So if you raise the k minus 1, it's going to coincide with the k. If you raise the 0, it's going to coincide with the 1. All of those are going to make something coincide with something else, right? So that's extremely helpful. This is just 0. And now we can write the k plus first term. Now that's sweet because that's just a single term, right? So that's going to give us C1 and then Mn down to Mk plus 2, and then k plus 1, k minus 1, down to 2 comma 1 comma 0, right? Because that just iterates this one up by 1, right? Yeah, and we'll assume that this one right here is like big enough that it won't make it 0 out, right? Because if this thing is k plus 1, right, then we would have just like stopped at k plus 1 instead of k, right? Like these are the ones that are consecutive, right? And then all of these are, there's at least a gap right here, right? Because otherwise we would have just like chosen it. We always choose it so that the first time that it's not consecutive is where we have this different naming convention, right? The idea here, I guess I'm saying it one more time, is we stack all the consecutive ones, and then this is the first jump that's non-consecutive. We would just rename k if this were something else. Okay, so that seems cool? Okay. And then after that, we've got the sum. Oh wait, this is attached to a number. This is attached to the number 1 over m sub k plus 1. And the plus 1 is outside of the index, right? Okay. No, it's just 1 over k plus 1, right? Because we're just going up by that, right? Yeah. Good. And then we have the sum as j goes from k plus 2 up to n of 1 over m sub j plus 1, and then we have c1 mn down to mj plus 1 down to 2 comma 1 comma 0, right? That's iterating these one at a time, right? Oh, I guess the important thing here, let's make sure we have the k down to 0, that it ends in that, right? Okay. So now also we have in parallel to this the derivative of c1 mn down to m k plus 2 k minus 1 down to 2, 1, 0. So that just iterates them one at a time, but gives you a coefficient of 1, right? So, and then whenever it acts on these, you get 0 for the same reason, right? So that's going to give us the c1 mn down to mk plus 2 comma k plus 1 comma k minus 1 down to 2 comma 0, right? And then plus the sum as j goes from k plus 2 up to n of 1 over, no, there's no coefficient, of cmn down to mj plus 1 down to k down to 1 comma 0, right? So again, it's like kind of gnarly, but that's what you get, right? And now we can finish pretty much everything off, like doing it the same way we did before, this like contradiction thing, which really limits the amount of like pure calculation that has to happen in the final argument. Before we do that, let's observe the following. And that is if we do k plus 1 what am I trying to do here? Oh, but yeah, I guess before we move on, I want to like pull something out of each of these sums. Let's start this at k plus 3 and pull the k plus 2 term off. So that's going to be 1 over mj mk plus 2 plus 1, and then C1 mn down to mk plus 1 plus 1, and then we have k down to 2, 1, 0, right? Something like that, right? And then we're going to pull off the same thing from here. That's going to have a coefficient of 1, though. So C1 mn mk plus 1 plus 1 down to k down to 2 comma 1 comma 0. And now we can do this combination. We can do k plus 1 times omega 0, 0, C1 mn down to mk plus 2, and then k down to 1 comma 0 minus the derivative of C1 mn down to mk plus 2, k down to 2 comma 1 comma 0. So that has the effect of canceling this thing out, right? Yeah. So that is going to give us, let's see, it'll give us k plus 1 over mk plus 2 plus 1 minus 1, because this coefficient right here, right, minus this coefficient right here, which is a 1, times Cmn down to mk plus 2 plus 1 down, and then k down to 2 comma 1 comma 0 plus the sum thing, right? Okay. And now we can like finish it all off. So the generators C1 mn down to m1 can be replaced with the single generator C1, and then this is going to be n minus 1, n minus 2 down to 2 comma 1 comma 0. Right, so where you just iterate up by 1 at each stage. And n minus 1 because they're n total things and we started at 0, right? Yeah. Okay. So now, how can we do this? Well, we're going to do the same kind of thing that we did before. So by way of contradiction, suppose not and A is chosen to be the smallest such that C1 mn down to, and I'm just going to put an A here, and then no, I'm going to put an A plus 1 here, A plus 1 here, and then k minus 1, all the way down to 2 comma 1 comma 0, can't be written with only let's just set that equal to C, okay? Or maybe just C1. No subscripts, okay? But then notice this formula over here, right? So notice this formula over here allows us to write k plus 1 over, this is going to be A plus 1, right, the way that we've written it, minus 1 times C m n down to a, and then k minus 1 down to 2, 1, 0 can be written as k plus 1 times this omega 0, 0 multiplying into C1 mn down to a. Sorry, this should be a plus 1 right here. A plus 1 down to a, and then k minus 1 down to 2, 1, 0, minus the derivative of that. So the derivative of C1 mn down to a, and then k minus 1 down to 2, 1, 0. And then minus this sum right here. Yeah, this sum right here, which, notice the way we've done it is the sum starts at k plus 3 and goes to n, and it does this thing right here. The important thing is that it's all happening to the left of where a is, right? So let's make sure to write that down really clearly, k plus 3 to n, and then mj plus 1, and then C1 mn down to mj plus 1, and then that's going to be down to a, and then down to k minus 1, 2, 1, 0. But now look at what we've done. We've taken our thing where a was the smallest number, where this could not be written in terms of just this generator, and we've written it in terms of things where the number was smaller, which means it can be written in terms of this generator, right? All of these can be written in terms of that generator by our assumption right here, because they're all smaller than the a plus 1, right? And a plus 1 is the smallest one that can't. So now we could say all of which can be written just with what we called C1. Contradiction. And that's the end of that. Okay. So now we can really sort of finish it all off. And that would be maybe done like this. F2 Z2 is strongly generated. Remember we talked about what that meant? It meant can be written as normally ordered polynomials by omega 0, 0, right? Which I'm actually going to give that a name, H, omega 0, 0, because it's actually a Heisenberg. It's a Heisenberg thing. C1, which is the normally ordered product of, well, actually, let's use what these are. Psi1, Psi2, right? So we don't have to use a crazy notation anymore. We've issued the need for that. And then this is going to be just simply the n minus first derivative of psi1 down to the derivative of psi1 and then psi1, right? That's what the subscripts gave us. And C2, which is the n minus first derivative of psi2. Now, we didn't do that, but that's completely parallel to what we just did. The same kind of, I bet the formula is exactly the same. There might be a minus sign or something. I guess like there should be something to be said about why this isn't 0. But it's not 0 because like we know that a plus 1 is not k plus 1. Because again, if a plus 1 was k plus 1, then we would have just extended further left where the consecutiveness stopped, right? Yeah, so that's why that is. Now, let's notice that we can say the weight of these. So of weight 1, so this is weight 1 because it's half plus half, right? And then we can calculate the weight of these as well. So what's the weight of this one? Well, they're both the same, but yeah. So check it out. It's going to be equal to what? So we've got n total things, right? And each of those things are weight half, right? So just from the number of things we have n over 2, right? And then we're adding all the derivative numbers, n minus 1, right? But then by, I don't know, intro to proofs class, what's this number?
I noticed the fraction thing.
So it's n times n minus 1 over 2. But notice that this just sums to n squared over 2. Yeah. So of weight 1, n squared over 2, n squared over 2. This is like kind of an aside. It's actually the lattice vertex operator algebra, v sub why am I? NZ. Yeah. Now you guys don't know what that is, but just like for completeness. Okay. Okay, so now let's recall this, that if we had dn, that was generated by our R matrix, which I'll just write as R again. And then also this matrix 1, 0, 0, minus 1, right? Now maybe we could call this matrix the S, like just that's generally what you would do with the dihedral group. And let's notice that S hitting phi1 just gives us phi1, right? Because remember, phi1 is just the vector 0, 1, 0. Yeah. And then S hitting phi2 gives us minus phi2. But now let's remember that psi1 was 1 over root 2 phi1 minus I phi2, and psi2 was 1 over root 2 phi1 plus I phi2. So that means that what does S do to psi1? What?
No, I'm saying because if
Just use this rule right here. Yeah, so what does it do to psi1? So it takes phi1 to itself, and it takes phi2 to its negative, but that's just that over there, right? So that's just psi2. And then s dot psi 2 similarly is just psi 1, right? So it just like does the switcheroo, right? Now, we can see now that what does s do to h? So it's going to switch psi 1 and psi 2. So what does switching psi 1 and psi 2 do to h? Or h? Yeah, it negates it because it anti-commutes. So that's negative h, right? And then what does s do to c? Well, this is kind of obvious, right? Right? It just swaps those, right? Yeah. And now you can do this whole game again. You can do this whole game again with like these h's, right? If you wanted to, like you could say like omega upper h, ab could be like the 8th derivative of h and the bth derivative of h, right? That's going to be an invariant under S, right? And it's already an invariant under R because this was supposed to be an invariant under R in the first place, right? And let's observe that like you could pare this down as well. I'm not going to do that. Like it's doing the same thing that we did before. And this pares down to maybe I'll just call it omega h 0, 0. And omega h 2, 0 for what it's worth. Yeah. Now that omega h 0, 0 is essentially equal to the Virasoro vector, right? So the L here is actually a half, and then I'm just going to put HH here. Yeah. And then you can write double, maybe we could say W was equal to the second derivative of H with H. Or we could add some more to it to turn it into a so-called primary vector. Maybe we'll talk about what that is a bit later. And so that takes care of what's going on with this right here. Okay? And now we have to figure out what's going on with this right here. But the game right here is actually kind of a little bit easier because we can use something about symmetric polynomials to finish this off quickly. So let's notice the following. And that is that what? Well, that like S dot C1 plus C2 is pretty clearly equal to C1 plus C2, right? Yeah, I think we can all agree to that, right? Yeah. And then S dot C1 minus C2 is equal to minus C1 minus C2. So it fixes this, right? And it negates this, right? So the fact that it fixes this means that maybe something that we would call just plain old C, which is C1 plus C2, would be another invariant with this dihedral group. Yeah?
Why not C2? The first one, why is it not C2 plus C1?
Where?
Like the first one over there? Like why is it not equal to C2 plus C1?
Well, it is, but addition is commutative.
Oh. In this case?
In all cases.
Okay.
Yeah.
Okay, but you just wanted it to be like that.
Yeah. Well, and that turns into C2 minus C1, but then you can see it like that. Yeah. But now let's look at this. If we were to do the following, if we were to do, so that sort of hints that normally ordered products of this with itself would be like new invariants, right? That kind of hints at that fact, right? Yeah. But the deal is if you take normally ordered products of that with itself, you actually just land back into the world where you have like these two h's next to each other. Now, maybe I won't check that here because it's like kind of gnarly with all the different things, right? But needless to say, you don't need anything like that. And I guess we could really spell that out by saying if we took the 8th derivative of c1 minus c2 times c1 minus c2, that's just going to be in terms of L and W, these two things over here. Now, but that means that like of the invariants that we might get out of these C-type vectors, we only get one new one, right? Because the other things that look like they might be new are actually not new. Because like, again, using stuff we've done before, this would be sort of an obvious choice because this gets negated, so it would turn into something like that. But then, like I said, you can do a calculation to see that this happens. Yeah. Okay. Now, that gives us like a kind of a bigger theorem. Not bigger. Which would be this. F2 dn, oh, this should have been an n up here, is strongly generated by L, which is a half HH, where H is defined as before, W, which is the second derivative of H plus some more terms to make it primary, whatever that means. And then the single thing C, which we'll define to be the C1 plus C2. Which, remember, C1 and C2 are these two things over here. Yeah. So now we can say the weights of these pretty easily. Of weight. So like this is weight 2, right? Because it's 1 plus 1. There are two weight 1 things, right? 2. This is weight 4 because it's two weight 1 things and then a second derivative. And then that's just, again, n squared over 2 because it's like you're summing two things of the same weight. That doesn't up their weight. Multiplying them ups their weight. So you have that. Okay. So now let's look at like a little bit of an application of this. That's a real math word, application. Let's look at this. We have a copy of Z4 generated by the 4 cycle, 1, 2, 3, 4, living inside of S4. Yeah. So remember, much earlier I said like, well, let's look at all these like subgroups of S4 and look for all the orbifolds of that, right? So this would be one of those. But this like falls apart pretty quickly with this thing that we've already done. It's just a special case of that. And the way that we can see it is like this. So let's notice that so let's say we've got F4, and we want to look at F4, Z4, right? And F4, we could say, is generated by phi1, phi2, phi3, V4 with the normal OPE. And here's what 1, 2, 3. Let's like call this thing sigma, so we don't have to keep writing the cycle, right? So here's what that does. So this is it just permutes the fields like it would from the permutation group. So it ascends the first field to the second field, the second to the third to the fourth, and this back here. So this would be like a picture of what this thing is doing, right? So now writing down some invariants without changing a basis is like kind of a pain. Doable, but like kind of a pain. And like I said before, there's a theorem that says if you have an abelian group acting on a vector space, which is what you have here, you can think about the vector space as just phi1, phi2, phi3, and phi4. You can always simultaneously diagonalize the entire group. So that means we should be able to simultaneously diagonalize this copy of Z4, but that's just diagonalizing this 1, 2, 3, 4 because it's a cyclic group, right? Now, thinking about, again, this phi1 as vector 1, 0, 0, 0, and all of these is your standard basis vector. So this is like in your brain box. This is how you're thinking about these, right? Well, then you can get a matrix representation of this sigma. And I don't know, it goes something like this. It goes like 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, I am a robot. No, but that's what it has to be. Because like, look, if we hit that into, is that right? No, no, it's the 4x4 sigma. So this thing should have the property that it maps this vector to this vector. This is the wrong thing. This is the inverse of this. So let's see, maybe it's like this. 1. Yeah, it's this.
Oh, I see now.
Yeah. Wait, no, it's not that. Why can't I make this work? No, this is right. This is right. So notice if you multiply this to, for example, 1, 0, 0, 0, you get 0, 1, 0, 0 by matrix vector multiplication, and then so on and so forth. So it does the right thing, right? And now, I don't know, you can find eigenvectors and eigenvalues of this, which I think we did one day, right?
Yeah.
We did that one day. So I don't know. Do we want to do that whole thing again, or? Okay, let's do the whole thing again. So I don't know. What do we want to call this matrix? A? Okay. So let's look at the characteristic polynomial. So that's going to be the determinant of xi minus a, right? But that's going to be the determinant of x, 0, 0, minus 1, minus 1, x, 0, 0, 0, minus 1, x, 0, 0, 0, minus 1, x. So it's like that, right? Then how do we find a determinant of a 4x4? Do you guys remember the name of the technique? You do cofactor expansion. So we'll expand across that row and that column first. And that's going to give us x times the determinant of this 3x3. Right? And then we'll notice the two middle terms are 0, right? So who cares? And then we'll expand across that. Yeah, it's going to be plus 1 because it's in the minus location. And then it has a minus sign as well. So it's going to be plus the determinant of minus 1 x 0, 0, minus 1, x, 0, 0, minus 1. Now we do that again, right? So we'll do cofactor expansion here like that, right? That's the only one we have to look at for that one, right? So that's going to give us x to the fourth in the end, right? Because it's going to be x times the determinant of this, but the determinant of that is x, right? Yeah. And then this next one, remember that you can do cofactor expansion across any fixed row or column. So we might as well do it across this column because it's got a bunch of zeros, right? Do you guys remember that? So we'll do it across this column. It's going to look like we're doing it across the top row, but we're really doing it across the column, right? And now look at what we get. We get minus 1 times the determinant of that. The determinant of that is minus 1.
It's 1.
No, it's...
1 times negative 1. 1, and then times it by that.
Oh, yeah. So we get minus 1 in the end, right? Good. And then, well, we can factor that fully as x minus 1, x plus 1, x minus I, x plus I. Right? And then we can go on the hunt for eigenvectors, right? So lambda equals 1. So that means we need to look at the null space of this with a 1 in it, right? So let's see, 1, 0, 0, minus 1. Like that, right? And now we'll do the same trick that we did before. We'll row reduce, right? Row reducing doesn't change the null space. So let's see. How do we want to row? I like to go from bottom. Yeah, so let's do row 4 plus row 1 becomes my new row 4. Right? Yeah, I guess that's like, I guess we'll do it kind of one step at a time. So 1, 0, 0. Remember what I'm going to do is I'm just going to write down blindly without really thinking, because you got to preserve your thinking, all the parts that I know automatically, right? So that's the first 3 rows and this one entry right here that we built the row operation out of. And then let's see, well, what do we get after that? Well, check it out. This is going to be still minus 1, right? And then 0, 0. Oh, thank you. And then what should we do from there? Row 3 plus row 4? No. Maybe swap row 4 up to row 2? Yeah. So row 4 swaps with row 2. Because I really don't like that 1 there, right? It shouldn't be so low. So that's going to give us the null space of 1, 0, 0, minus 1, 1, 0, minus 1, 0, negative 1. Oh, wait.
No, row 3 stays the same. 0, negative 1, 1, 0. You're stopping row 4 and row 2.
Oh, that's dumb though, because row 2 has an issue too.
So it would be
We
row
should
3
do,
and
we should do row 3 and row 4. Gosh, what's wrong with me? Do you know? And then what goes here?
0, 1, 0.
Oh, and then
We can add row 3 and 4. And put it in row 4.
yeah. So let's do row 4 plus row 3 becomes my new row 4. So that gives me 1, 0, 0, minus 1, minus 1, 1, 0, 0, 1, 0, minus 1, 0, what? 1. Good, like that. Oh, but now notice this is a multiple of row 2, right? Yeah, that's a multiple of row 2, so I'm just going to erase it. Because I can do that, right? And then what should we do from there? Add row 2 and 3? Should we do that? That.
Oh, okay.
So 1, 0, 0, minus 1, minus 1, 1, 0, 0, 0, 1, minus 1, 0, 0, 0, 0, 0, right? Something. Yeah. So yeah, row 2 minus row 3. Is that what you said? Yeah. So that gives us, becomes what? Becomes new row 3?
Yeah.
Yeah. So that turns into the null space. This is the worst part of linear algebra class. Jeez, I hate it. So what does that give us?
Negative 1, 0, 1, 0. But then we can subtract 1 and 2, 1 and 3.
Is that what you said? Yeah, so let's do row 1 plus row 2 becomes new row 2, and row 1 plus row 3 becomes new row 3. Oh, and then we're home free. So that gives us the null space of 1, 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 0, right? Yeah. So that means that this is our free variable, right? Because it doesn't have a pivot, and these are our non-free variables. And then if we hit this with the vector x1, x2, x3, x4, right, we'll see that x1, x2, x3, x4 satisfies x1 equals x4, x2 equals x4, x3 equals x4, right? Because if we multiply that into this, you get that kind of system of equations, right? Keeping in mind that it's in the null space, so being in the null space means that it multiplies to give you 0, right? So now we might as well take x4 to be a half. Let's turn it into a unit vector, just all at once, right? And we get 1/2 right? But now, in terms of the VOA, that motivates us to perhaps set psi1 equal to 1/2 phi1, phi2, phi1 plus phi2 plus phi3 plus phi4, right? And then let's observe that sigma takes psi1 simply to psi1. It fixes it, right? Yeah. And then I'm not going to do the rest of these. It's like so much. And in fact, like, you can almost just write these down. Like, there's like it's kind of a format. So let's take, well, I erased my thing. We're setting sigma equal to this. And let's take psi1 to be a half phi1 plus phi2 plus phi3 plus phi4. And then I'll teach you guys the format for this, like after I get it written down. It works actually for any like n cycle in Sn. And then we'll take psi2 to be a half phi1 minus phi2 plus phi3 minus phi4. And then we'll take psi3 to be equal to a half, and then phi1, I think it's plus I phi2 minus phi3, and then minus I phi4. And then, psi4 is a half, and then phi1 minus I phi2 minus phi3 plus I phi4. So the idea here is that these are all of the form like this. These all look like, let's see, phi1 plus some power of I, maybe I to the k times phi2, plus I to the 2k times phi3, plus I to the 3k times phi4. They all look like that. It just for different values of k. And I didn't number these like where the k's correspond to the indexes, the indices or whatever, but you could make it correspond to the indices. And in general, what it is, it's like this. You have phi1 plus eta to the k times phi2 plus all the way up to eta to the n minus 1 times k phi n. That's what it would look like in general, where eta is that nth root of unity. And you get n different vectors like that. But anyway, it's kind of neither here nor there. Now let's look at what happens. What does sigma do to psi1? Well, it goes to psi1, right? That was our point, right? And then what does sigma do to psi2? So remember, exactly, because it's since phi1 to phi2, phi2 to phi3, yeah, so it sends something to its negative psi2. And then what does sigma do to psi3? Exactly, it multiplies by negative I, minus I psi3. I guess the easiest way to see this is to see what's happening here, right? Yeah. And then sigma dot psi4, well, there's only one thing left. There's only kind of one logical choice, right? It's like that, right? Now, in general, you would have something like this happening. Like if you had like 1, 2, 3 up to n or whatever, you would have, after this diagonalization, you would have one thing fixed, one thing going to the first power of that root of unity, one thing going to the second power of that root of unity, one thing to the third, so on and so forth, all the way up to the n minus first. Yeah. But the cool thing here is the following also. The OPE, so psi1 z, oh, psi1 with psi1 is 1 over z minus w. So this thing is like kind of on its own, right? It's like been partitioned off. And then I think you can check psi2 of z with psi2 of z is also 1 over z minus w. Now it seems like it's been partitioned off, but it really hasn't been. It's been partitioned off a little bit, but it's still getting acted on by sigma, right? So in fact, the action of sigma on psi2 gives us this f1z2 that we did before, right? Yeah, we did that one before, right? Yeah, and then psi3z, psi4z is the one that's 1 over z minus w. And then 3 with 3 and 4 with 4 are both 0. So these are all the non-trivial ones, right? But check it out. Look at it. This right here, with this OPE is exactly a copy of F2Z4. Right? Because the sigma 3 and sigma 4 form a copy of S2 of F2, and then Z4 is acting on that just the way that we did before, right? And then this thing right here is a copy of F1Z2 for the same kind of reason. And then this thing right here is just a copy of F1.
So our project is to look for a copy.
No. So now we want to like minimize these generating sets, right? I mean, we haven't written down what the generators are, but we can actually do that. Like it's not so bad. Like notice that the generator for F1 is just phi1, right? We had that before, right? That there's nothing touching that. It stays the same. And then the generator for F1Z2, again, we did that before. That was just a half del phi2 with phi2. I mean, we called it something different, but that's what it ended up being, right? Yeah. And then the copy of F2Z4 is going to be this normally ordered product of sigma 3, sigma 4, right? And then I'll call this C3 and C4, which the C3 is simply the third derivative of sigma or psi 3, the second derivative, the first derivative, and then the no derivative, right? It's our thing that we had before. That before it was like a degree n thing, right? But now it's just a degree 4 thing. Should it still be called C? Because C meant cubic before? Should it be called Q? I don't know the answer to that. What do you guys think? For quartic? Do you want me to change it to Q? And then Q4 is the same, right? With just a different index. And now you might be like tempted to say, well, I'm good, I'm done, right? Because I found all of these generators in the past, right? So maybe, so here's the temptation. And that temptation is to say that because of what we have before, this F4Z4 is simply generated by everything we have on the board so far. In other words, phi1, a half a normally ordered product of d phi2 with phi2, this q1 and this q2. That would be the temptation, right? Because like, look, we were able to pretty reasonably decompose this into a special case of that long problem that we just solved, right? But you'd be incorrect, because there are some more. There are some more, but there's not a ton more. And they're kind of easy to find. Does anyone see something that you would also get? Keeping in mind that what we want to do is take products, if you will, of phi1. We don't need to use phi1 because like it's always fixed, right? So products of phi2, 3, and 4, so that when you hit it with sigma, it doesn't change. Sorry, psi. Oh, I just changed. This should be a psi. Hopefully you guys did that when you wrote it down. That was my bad. Okay, so does anyone like have so some products of psi 2, 3, and 4, so that when you hit it with sigma, nothing happens. Well, something happens, but it's just the things that happen multiply together to give you the number 1. Yeah, we already got that though. But that's good thinking. Yeah. So we already had that. So just to recap, we already have that. We already have essentially what's the square of psi 2. This is essentially the square of psi 2, right? And then we also have the fourth powers of just psi 3 and psi 4. Is there a way to combine? There's two more ways. Just like, spoiler alert. So you can recast this problem as like, take the numbers I, minus I, and negative 1. And how can you multiply the numbers I, negative I, and negative 1 to give you the number 1? It's the same problem. So how can you do that? So we've already seen that minus 1 squared is 1, right? And that I to the fourth is 1. So is there another way to multiply those numbers to get 1? We got that. We got that. Okay, well think about this. We've got a negative 1. Can you get another negative 1 without using directly this negative 1?
We can square.
Yeah, exactly. So there are our more. We would maybe write them like, they would be something like this. dA psi 2, dB psi 3, dC psi 3, right? So notice if we hit this with sigma, minus 1 and an I pops out. So you have minus 1 times I, that's positive 1, right? And then also, there's the companion of that, which is dA psi 2, dB psi 4, dC psi 4. Right? And then the interesting thing about this is that we can minimize it just as we did before. Maybe that's the next thing to do. I'm trying to be more hands-off after today. So doing the same kind of thing that we did today, right, and in the past week, minimize this down to something. I can tell you what the conjecture is. Yeah, exactly. But notice if you take the normally ordered product of this with itself, you get 2 psi 2s and 4 psi 3s, right? So it's the same thing as taking the normally ordered product of this with one of these, right? So it's a little different. You actually never have larger powers of that. You just have those. That actually means that like the whole thing is gonna, this is actually a subalgebra of this. And the whole thing decomposes like a module of this thing, whatever. Don't worry about that so much. Yeah. So here's my conjecture. I mean, if anything is like kind of obvious, is we only ever need one thing, right? The obvious thing is we only need, maybe we'll call these C's now since we've changed the other thing to Q. We only need C, I'll call it 3 because this uses more 3's. And then let's say that this is psi 2, the derivative of psi 3 with psi 3. Notice we have to have a derivative there because you can't have 2 psi 3's, right? Yeah. And C4, which is psi 2 with the derivative of psi 4 and psi 4. Okay, so now here's like what I want to move on to doing now that we've put a cap in this, is that I want to look at